this AKBL dot AUBV. K plus U, we have that V plus minus 1 to the power U plus L. Yes. So now you see that actually we have associative law to be true. Hence, the operation dot is associative. One can verify that A0 B0 acts as an identity. Give me a moment, okay. One can verify means, let us just quickly see whether that is the case. Say we take AIBJ. Now according to our definition we will have A0 plus I, B, J plus minus 1 to the power I plus times 0. And this turns out to be AIBJ. But that is not enough. We have to see the other one also. Or we could have seen the other one and the fact that there is a right inverse, because according to one of the exercises that we have solved previously, a right identity and right inverse is enough, they are enough. But anyway, I plus 0. Okay, now here what we have, 0 plus minus 1 to the power 0, 0 plus minus 1 to the power 0 times j. Now minus 1 to the power 0 is 1. So again we are having this. So yes, this acts as an identity. And the inverse of this, it actually has two expressions which are, I forgot what is that expression. Yeah, here it is. Minus I minus j if I is even. So it depends on the parity of I, and it's the same thing if I is odd. Since we are verifying everything, so let's just see this one also. Ideally we should show all these things, but to minimize space while typing these solutions out, I compressed things. So what happens when we operate these two? Say I is even, okay. Under that condition, the first one is of course I minus I. What about the second one? Minus j plus minus, oh, b, okay, now I understand. Because this part will appear as an exponent for minus 1. So that's why we need to see whether it is even or odd. Now since I is even, minus I is also even. So it gives us minus j plus j, and we end up having this, the identity element. What happens if we come from the other side? Here we of course have a0 because minus I plus I. What about the superfix of b? Now we have j plus minus 1 to the power I times minus j. This and this. So here also, since I is even, this will be plus. So that means we will have minus j. So j minus j is this. So yes, when I is even, this acts as an inverse of aibj. When I is odd, then the element is its own inverse. In this case, since we have the same thing, it's enough to consider only this one, because if you change the order, nothing changes. Okay, however, what will happen here? I plus I. I plus I is, okay, let us just first write the expression and then we will see. J plus minus 1 I to the power I times j. I plus I is even, after all it's an even integer, so we can, in place of I plus I, we can write 0. Why? Can you guess why? What will happen here? We don't have to write 0, we don't have to bring 0 from outside, but this becomes 0 because now I is odd. So minus 1 to the power I will be minus 1. So j minus j is 0. Actually, we can write one more step. We have this, however, this is equal to a0 b0. Why? Because this is related to a0 b0. This part we understand. 0 is congruent to 0 mod n, these two superfixes. However, what about this one? Is 2i congruent to 0 mod 2? Yes, because 2i is divisible by 2. 2 is appearing, so although I is odd, but that does not matter. So yes, this is also an expression, namely the element itself is its own inverse if I happens to be odd. So that these are all the 4 conditions you need to call a system a group. Hence, G forms a group under the operation dot. Now we have to see that this group is non-abelian. Note that let us calculate this product. A0 BR, let me write from the next line. A0 B1 dot A1 B0. What shall we get? Zero plus minus 1 to the power 1 times 1. So here we are getting A1 B. This one will be minus 1, so we get minus 1. And what shall we get if we switch the order? A0 B1, and this becomes equal to A1 plus 0 B 1 plus minus 1 to the power 0 times 0. So this becomes equal to A1 B1. Now are these two things equal? If they are equal, then we cannot draw any conclusion, but if they are not equal, then we have got non-abelianness. Since n is greater than 2, we have A1 B1 not equal to A1 B minus 1. Why is that so? Because you see, for these two congruence classes to be equal, the representatives should be related. Had this been the case, is it the case though? 1 is of course congruent to 1 mod 2. We are talking about these first two superfixes. However, is 1 congruent to minus 1 mod n? If I want this to happen, what does it mean? N has to divide 1 minus minus 1. That is, n has to divide 2. However, it is given in the question or given in the exercise that n is greater than 2. So it cannot divide 2. So that's why we are writing, since n is greater than 2, these two things are not equal, and hence the group is non-abelian. Hence, G is a non-abelian group. Okay, and that ends the solution. So we have constructed a non-abelian group with an extremely strange looking binary operation. Later, in some other videos where we will study higher group theory, we will come to know that this is actually a semi-direct product of two groups. We will see those things. Now let us come to the next exercise. Here we address a question which arose when we were talking about the associative law. We said that there is a general associative law which allows us to write a product of any finite number of elements in a group without using brackets. In other words, it says that whatever way of bracketing we adopt for such a product, the ultimate result is going to be the same. So this exercise asks us to prove just that. So let's see how this exercise is stated. We don't even need full group structure in the set for this to happen. We only need the associative operation and the fact that the set is closed. That is enough. If S is a set closed under an associative operation prove that no matter how you bracket, a product like this, where of course you have to understand that this A1, A2, these are coming from S, retaining the order of the elements. You get the same element. Note that retaining the order of the element means we cannot change the positions of these elements. We can bracket them in whatever way we want, but we cannot change the position because we are dealing with an associative operation which may or may not be also commutative. If it is commutative, then order will not matter. However, in general, order matters. The same element in S. There is an example also. Example A1, A2, A3, A4. Say someone has written a product of 4 elements like this inside 2 brackets. This will be equal to, if one wishes, one can apply associative law again and again to see that this will be equal to this, and a hint also is given: use induction on N, and that's what we are going to do precisely. So here the solution is neither very difficult nor big. We apply induction on N. If N is equal to 1, that is, if there is only A1, then there is only one way of bracketing A1, namely this, and we have nothing else. So here the result is trivially true. In fact, you cannot even say anything because there is only one element which can be, you can bracket it, or you may wish to not use any brackets. After all, you are getting A1, whatever you do. So the result is trivially true in this case. Trivially true, and in fact somewhat a little foolish also. So this forms our basis for the induction. Now we are going to assume the induction hypothesis. That the result is true for a product of any L elements of S for all values of L, where L is an integer lying between 1 and n, where n is some positive integer. So here we are going to use strong induction because we have chosen an induction hypothesis like this. So what we are saying here is that the result is true for a product of any L elements from S. If you take L elements from S and you decide to bracket them in any way, you are going to get the same element of S back. And L itself can take value from 1 through n, where n is some positive integer. Now based on this assumption, we have to prove that the same is also true for a product of any n plus 1 elements in S. Now let A1, A2, etc. till an plus 1, these are elements in S. Okay. We consider the following different ways of bracketing the product. What is our product? A1, A2 up to an plus 1. And what are the two different ways? Actually, two different ways we are going to consider of bracketing the product. One of them is this: A1, A2 up to AS dot AS plus 1 AN plus 1 and A1, A2 up to AT dot AT plus 1 AN plus 1, where yes. Okay, so now we have considered this product of n plus 1 elements in S, and we have chosen two different ways of bracketing them. Now note here carefully that this is T. These are integers S and T which are different. So because they are different, one of them will be smaller than the other. So we have chosen without loss of generality that S is smaller than T. Now what is the meaning of these things? Both of these things are this. However, we have put brackets in separate places. Depending on the values of S and T, we have decided to end the bracket here, first bracket here, right after we have AS, then start a new bracket from AS plus 1, and then we have AN plus 1. Okay. Now, and same for T. However, what is the meaning of these products, these four products? How are they being bracketed inside? And the answer to that is that we don't care. Why? Because you see, S is lying between 1 and n. So what is the maximum value of s? What do you think the maximum value of s will be in this situation? Note that s has to be strictly less than t, and as such s has to be strictly less than n also. So the maximum value s gets is n minus 1. Now for that value of s, if we look at this product a1, a2 up to an minus 1, this product does not depend on the way we bracket it because of our induction hypothesis. You see, if you take a product of any L elements, no matter however you bracket it, you are going to get the same thing. So without writing any way of bracketing this product, this is well defined for L equal to n minus 1. If this is well defined, then the smaller products where we have less number of factors will also be well defined because of our strong induction hypothesis. Okay. Now how large can this second product be? For that to happen, s has to take the smallest possible value, and that smallest possible value is 1. If we do that, we have this product. How many factors are there? Starting from, if we had 1 here, we would have had n plus 1 factors, but now we have n factors. So this product has n factors. So for L equal to n, according to our induction hypothesis, this is also well defined without specifying any particular way of bracketing it. And the same is true here also, although it will be slightly different. What is the largest value of t? The largest value of t is n. So here in the first product, the largest it can ever get is this, still within this range. Okay, so it is taken care of by our induction hypothesis. It is well defined. What is the smallest value of t? The smallest value of t, see, t has to be strictly greater than 1, so the smallest value of t is 2, and we get this one again. Okay, so all these products are well defined. We have only shown the outermost way of bracketing this product in 2 different ways. Inside what is happening we don't know, and we don't need to know. But we should nevertheless mention that, note that by the induction hypothesis, the products, we have 4 products here, AS plus 1 to AN plus 1, A1 to AT, and AT plus 1 to AN plus 1 are well defined. So we are not making any mistake in writing them simply like this. Now we have to say that these 2 ways of bracketing ultimately give us the same thing. AS plus 1, AN plus 1. Okay. T is greater than S, which means what? Since T is greater than S, T will appear here somewhere, isn't it? I mean here as a suffix t will appear because t lies between 1 and n. So note that t cannot be n plus 1 because we are writing t plus 1. So do you see the reason for this upper bound? We have n here because we have t plus 1 here. So if t takes the largest value, then we have to have that thing available for us, and that is a n plus 1. So t appears here somewhere, and because s is less than t and s and t are integers, so s plus 1 is less than or equal to t. This is strictly less than t. If you add 1, either it becomes equal to t or it still stays less than t. So that means this product itself can be written like this. A n plus 1. Now what have we done here? Whatever we have done, is it justified? Let us see. We are right in writing t here in between somewhere. There is no problem with that. However, note that this product has now been written in this way. This itself has been written in a bracketed form, and that can be done because of our induction hypothesis. This is one of these products, no? This one. So according to our induction hypothesis, we can bracket it in any way we want. Its length is less than n plus 1, that's why. And also s plus 1 is less than or equal to t, so no problem. In the worst case scenario, s plus 1 will be equal to t. So here in the first part, you have only a t. Fine, no problem. And now you use our ordinary associative law. Doing that, we get as dot as plus 1 to a t dot a t plus 1 to a n plus 1. Whatever arguments we have used here to write this product in this form, a similar argument applies now here, and this product ultimately can be written like this. Because this is also one of those products, this one, and since s lies between t and 1, so s appears here somewhere, it has appeared. So this is actually a particular way of bracketing this product, and that gives us the same result. It just gives us this product. If we used some other thing, some other way of bracketing this product, that also would have given us the same result. Here, however, this gives us this. So that's it. These two elements are equal. So two different ways of bracketing have led us to the same element, and these were general ways of bracketing. Okay, so we have in fact achieved what we wanted. This completes the induction. This result has a name also. It's called General Associative Law. This completes the induction, and that completes the solution also. Now because of this exercise and we have solved it, inside a group we will now, while writing a thing like this, we will not bother to write brackets because we know that this is well defined. We will not use brackets anymore unless we absolutely need them. Okay, so this was 19th, and now we come to matrices, groups involving matrices. So this is exercise 20. These exercises have been written like this with a hash symbol. It represents the fact that these exercises or the solutions to them need a preliminary knowledge of matrices. So assuming that you know about matrices, about their addition and multiplication, which you probably already know because matrices make their entries quite early in schools right now. So based on that preliminary knowledge, you have to solve these exercises. So the first one goes like this, for which actually we won't have to do anything because we have already done it. Let G be the set of all two by two matrices A, B, C, D, where A, B, C, D, this part, what I am writing right now is not there in the exercise.